Welcome. Here we're going to be looking at multivariable optimization. So I'm looking to find the minimums and maximums of a function that is dependent on two variables. So I have x and y both in my function. So I'm considering this example, f of xy equals x cubed minus 8x plus 2y squared. I have graphed it here in the upper right hand corner. And so if I'm looking at this contour plot, minimums and maximums occur in the center of locations that have concentric circles. So I'm going to have something here in the middle of these concentric circles. Because my numbers are going down, I have 20 and then 10, 5, 0, and then negative 5. Looking at my contour only, this is going to be a minimum. And then I also will have points of interest anywhere that my contour lines kind of come in together. So we see these contour lines here for the 10, they're sweeping towards each other. If the same number ever crosses each other or just comes close to touching, that is also a point of interest, and that's going to be a saddle point. If you're unfamiliar with horses, and you don't really have a strong feel for what a saddle looks like, you can think of a Pringles chip, which is also a delicious way of remembering what a saddle point looks like. So it means that the function is going down towards one direction, and in the other direction, it's coming up. So that's what that will look like. So I know what I have just based on my contour plot here, but let's go ahead and do it algebraically, because also these are estimations. I know that my point is somewhere here. It's going to be, I don't know, around 1.5-ish, maybe a little more. And then same here, it's going to be the x value is going to be around negative 1.5, a little bit higher maybe. But we do want to be able to find the exact values algebraically. So when we're looking at multivariable optimization to find these mins and maxes, we're going to perform a test called the second derivative test for multivariable. So the first thing I need to do is find my critical points, which we still do using the first derivative. So my first derivative though, now because I have two variables, I will consider my first derivative with respect to x and also with respect to y. So I'll take the first partial derivative here with respect to x. I will hold the y, I force the y variable to be constant for this operation, which is why we treat it as a constant, because I'm forcing it into that position. So I have 3x squared minus 8, and then the 2y squared, because I'm forcing it to act as a constant, goes to 0. And then when I take my derivative with respect to y, I force my x to be constant. So my x cubed and my minus 8x, both of those go to 0, and I end up with 4y. So similar to when we do single variable, multivariable, we need to set each component set equal to 0. So I should have said this. We're finding the critical points. And the first step is to find f of x and f of y, so that first derivative. The next thing we're going to do is set each equal to 0. So I have 0 equals 3x squared minus 8. When I solve this, I end up with 8 equals 3x squared, so 8 over 3 equals x squared, and then when I take the square root, I end up with plus or minus 1.633 equals x. Do be careful, you do need to consider the positive and negative. When I set 4y equal to 0, I just get y equals 0. Now, I need to take all the combinations of these in order to get all of my points. So I will pair both of my x components with my y component. If I had a second y value, then I would pair both of them with each of the y and end up with 4 points. So be careful, you do need to consider all the possible combinations. So the critical points negative 1.633 and 0, and then positive 1.633 and 0. So that's my x-coordinate and my y-coordinate for my critical points. So that's a good start. Those are those points of interest. So that corresponds to these two red dots on my graph. It's the 2 points of interest. Now I need to evaluate what is happening at each of these critical points, and I will do that using the discriminant. So I'm going to try to fit this all on one page here. We'll see if we can manage that. The second step is to evaluate the discriminant for each point. Now, we call this the discriminant because it helps us to discriminate what is going on at each point. So for each of these points, I want to know what's happening to the concavity. I want to know if the concavity is uniform, meaning it's all the same direction no matter where you go. So if I'm looking in a full 360 circle, if I were standing on that point, a full 360 circle, it would either be concave up or concave down for that entire, if I spin around, right? If it is not uniform, then that means it's a saddle point. If it is uniform, that means we need to then determine whether our concavity is up or down, and then we'll have our answer to whether we have a max or min. So the discriminant of any point, let me just do it in generic terms, xy, is going to be equal to the second order derivative in terms of x times the second order derivative in terms of y minus the second order for xy squared. So this is the formula I'm going to use. So I need to first find all three of these components. I have only first derivatives. I have not yet taken the second derivative of in any direction. So first I'll find those three things. So the second derivative in terms of x, I already have f sub x. That's 3x squared minus 8. So when I take the derivative again with respect to x, I end up with 6x. When I look at the second order derivative in terms of y, f sub y is 4y. So when I take the derivative, I get 4. And then I'm looking for fxy. You can actually do either of them. For smooth functions, they will end up being the same thing. So you could either take the derivative with respect to this f sub x and take its derivative with respect to y, or you can look at f sub y and take its derivative with respect to x. Either one will actually get you the same answer. So if I look up at f sub x, there are no y's in this at all. I'm over here back in my step 1. There are no y's at all. So when I take the derivative, it is just 0. And the same if I were looking at my f sub y, there are no x's. So if I took the derivative of that with respect to x, I would get 0. So I should get the same answer no matter which way I go. But the discriminant then is going to be 6x times 4 minus 0 squared, which will just be 24x. This is the thing that I am now going to evaluate for each of my 2 critical points. And it turns out I'm not going to be able to fit it all on one graph. So let's scroll down a little. Or one page, I should say. So let's go back over here. We're evaluating our critical points. I shouldn't have a step 3. This is step 2 continued. So the discriminant for negative 1.633, 0. I don't have any y's, so it's just 24 times negative 1.633, which gets me negative 39.192. Okay, this is negative, which means that my function is not uniform around uniform concavity around that point. If it is not uniform concavity, that means it's a saddle point. So in the terms of trying to find local mins and maxes, that point is out of the running. It is a saddle point, and I don't need to worry about it anymore. When I evaluate the discriminant for my positive value, I get the same number, just positive. So positive 39.192. Okay, so now because it's positive, it means that it is uniform concavity. So it could be still concave up or concave down. I haven't determined that, but it means that there is an extrema here. The fourth step, or not the fourth step, the next step is to determine whether we have a min or max. And we will do that by plugging in this value, this point. So I'll plug in my point to either f sub xx, so fxx, or fyy. Either one will work. It doesn't really matter, because no matter what direction I go in from this point, I know that the concavity is uniform. So it doesn't matter what direction I go in, my answer will be either positive or negative uniformly. So I'll just pick the one, I usually pick the one that's easier to evaluate. And actually, f sub yy equals 4, so it's always positive. If you evaluated fxx, you would be evaluating for this location. So that was 6x. So it'd be 6 times 1.33. You're putting in the x and y value of that critical point. There's no y's. And you would get 9.798, which is still positive. So for either of these two things, I'm seeing that I have that positive value, and this is my concavity. So if it's positive, that means that I'm concave up. And a concave up function will correspond to a local minimum at the point 1.6330. And then you have a saddle point at, I should have written that's here, negative 1.6330. So those are our two locations of interest. If I scroll back up, I can see that that's what I had, right? So I had a positive, I said it was about 1.5, but yeah, it's close, right? My exact value is 1.633. This is my local min. And then my saddle point over here at negative 1.330. So that's how we handle multivariable optimization. In general, you will either, I should cover one special case of the discriminant. So in this instance, I had one discriminant value that was negative, and that corresponded to my saddle point. So that's what's happening here when it was negative. I had one discriminant value that was positive, and that corresponds to an extrema. I had to do a little bit more work to determine whether it was a local min or a local max. You can also have the discriminant being equal to 0. So if the discriminant is equal to 0, the test is inconclusive. At that point, the easiest thing to do, or maybe not easiest, but the best thing to do, is going to be to graph it in a 3D model and actually look at your 3D model to see what is happening at that point of interest. Because you should be able to tell just based on the model whether you have that saddle, that min, or that max. So that is how we handle multivariable optimization. So we're looking for those extremas for a multivariable function. Thank you so much.